So, okay, let's begin today's session. This is week 7 of complex analysis course. So, we'll see what happened this week, and after having sort of summary, we will solve the assignment problem. Okay, so the week started with Cauchy integral formulas. Cauchy integral formula. So, what is Cauchy integral formula for analytic or holomorphic function? So, this week we have found that holomorphic and analytic both are same. Analytic means in a neighborhood it is given by a power series. So, let's start with Cauchy integral formula. What was that? It is when omega subset of complex number, open connected subset. Connected we don't need open subset. We just require open subset here. And there is not a point inside omega are positive such that D did not R this is contained inside omega. F a function which is holomorphic. Okay, so F holomorphic on F holomorphic on omega, then the values of F can be determined by the integral over various curves surrounding Z naught. So what I mean, then F of Z naught can be calculated in this way. Of Z is equal to 1 upon 2 pi I integral over gamma of F of Z divided by Z minus Z naught dz, where gamma is gamma of Z is gamma of T is nothing but Z naught plus R e power I. Okay. So in place of gamma, we can take any other curve gamma prime, which is uh, homotropic to gamma. So that doesn't change the integral. So f of z can be calculated in terms of integral. So this is Cauchy integral formula. So after proving this formula, what we have seen is that in an when function is holomorphic, so this is, let's say, first part. Second part is uh, f holomorphic. Then in same situation is, let's say, same omega is open connected subset or open subset of C, and dz not R is contained inside omega, then F is holomorphic when F has uh, power series representation. uh, Power series presentation or power series expression in any disk inside omega. Okay, so this is that F is holomorphic, then F has power series expression, and once power series expression as a corollary of uh, this 2a, which is F is holomorphic, then F prime is also holomorphic, right? So these are some results which I am just mentioning uh, so that they will be helpful to remember while solving the question. And once f is holomorphic, it is infinitely differentiable. Same using 2a again and again repeatedly. Right. So after this corollary, we have seen factorization theorem. What factorization theorem is? Factor theorem. This is basically, I'm not writing all these things, but I think that will be clear to you. F is holomorphic on omega, f from omega to the holomorphic such that f of z naught, one point inside omega, is equal to 0, then there exists unique G holomorphic such that f of z is nothing but z minus z naught into G of z. Right. So what the proof is like, get a power series expression for fz, and you will see that because f of z naught is equal to, so you have to take uh, expansion around z naught. So you will not having constant term. So your power series expression starts from z minus z naught is first element by 1 factorial, z minus z naught squared divided by 2 factorial, this way. So you take z minus z naught common from the whole power series, and whatever is left inside that power series, because they have same coefficient, so ratio test or some test will imply that the power series inside the factor is convergent. So you did just define that function to be TJ. So that's the proof of this. Right. After factorization, NLT continuation. What was NLT continuation? Principle of NLT continuation, or principle of principle or principle of NLT. This is like if the two functions f c from omega to c, holomorphic holomorphic uh, function such that f is equal to c uh, on an open subset of omega, open subset of omega, then f is equal to g on omega. They agree on full set. Okay. After this NLT continuation, we saw that zeros of the zeros of holomorphic functions are isolated, discrete or isolated, whatever. So only zero function is function uh, which has zero with zeros limits inside this set of zeros. Okay. So if what I'm saying, if uh, the set of zeros has limit point inside omega. Okay, inside omega, then f is 0 function. Okay, right. Now what is next result about? After this, I think Liouville's theorem and Morera theorem. These were two big results. So we'll also see them. Okay, I need one more page here. Right. So fine. Set of zeros. They do not have limit points inside omega for non-zero functions. Using this, what we can say, if two functions agree on a dense subset or subset where they have limit points, they are same. Okay. Just using 5a, we have a corollary 5a such that if f and c from omega to c holomorphic, such that uh, f f of z is equal to c of z, z belonging to omega, this set such that this has a limit point. Then you just calculate for fz minus gz using f minus g, this function. We see f is equal to g on omega. So both functions coincide because this becomes 0 on a set where we have a limit. Okay, so these results and Liouville's theorem, this uh, Liouville's theorem. What was Liouville's theorem? It is about a function is a bounded. A function is bounded. An entire function, an entire function which is bounded is constant. Okay, so the proof here, I think we required some uh, bound on so some bound on f. So how is the idea of proof? We get a power series representation of function f everywhere, and we want to calculate what is f prime at given point z naught, what is f double prime at given point z. So you just see that f prime is completely zero, hence f will be constant. How f prime will be zero? So f prime of z naught is when given by one of the formula. If you remember, it is 1 factorial divided by 2 pi I f of z, sorry, f of z divided by z minus z naught square, the integral over gamma dz. Okay, so where gamma is gamma of t is centered at z naught, any radius, you can take r, all right, t belonging to 0 to 2 pi. Okay, so what happened from here? We calculated modulus of f prime z naught. This is bounded by, because f is bounded, which is bounded, uniform bound we have. So it is always bounded by m divided by 2 pi. I has modulus 1, so that is gone. Z minus z naught is always, so the z is running in gamma, which is a circle of radius capital R. So z minus z naught has always distance r, so r is square, and fz is bounded by m, so m is in the numerator. Now what extra is left is the integral of 1, which is the circumference of the circle, which is 2 pi r, right? So which is equal to 2 pi get cancelled, m by r, and because r we can choose arbitrarily large, so this will imply that because f is entire, we can choose as large as possible r. So f prime z naught is 0. This will imply f prime z naught is 0, r tending to infinite. So since f is entire, we can choose so. So f at z naught we have calculated derivative 0. Similarly, at any point z naught, because z naught was arbitrary, z naught belongs to C, and f prime is z naught is 0, so f is constant. This was the proof of Lewis theorem. How? So once f prime is 0, then we are done. It is constant function. Right. Using Lewis theorem, we have seen corollary of 6. It's 6a, which is fundamental theorem of algebra. Fundamental theorem of algebra, which is saying that a polynomial of degree n has n roots, possibly not distinct, means some roots can repeat. So this proof was clear that if f, so if a polynomial nowhere one exists, what happens? 1 by p defines the whole entire function because it is branching nowhere. So we somehow show that 1 by p is constant, hence p is constant. Okay. So what is the idea of the proof? Let p z p n degree polynomial, poly n bigger than 1. Okay. Then p has a root, and then we use factorization theorem. So once we have a root, z minus z naught is a factor of p. So what is left is degree n minus 1 polynomial. So we again find a root for that, and by it repeated iteration, we get a factorization of p, complete factorization. So we just need one root is there, c. So then p has a root c. So proof is obvious. So using Lewis, the idea is if pz has no root, then what happens? 1 upon p there is entire function, and this step is crucial. So using Lewis, so you have to say it is bounded also. The boundedness is some estimate. Use Lewis theorem of 1 upon p z is constant. 1 upon p z is constant. This will imply p z is constant. So actually, what is idea of the use how to use Lewis theorem is we have to show pz is bounded 1 upon pz bounded. So in a disk of radius r, so if you take closure of that, it is just compact set where it is already bounded. So in the complement of the disk, we show that this is a bounded function. Okay, so that is the proof you can find it. But I am just giving you the idea of how is the proof, how was the proof of this. So the next thing was about Morera's theorem, 7, Morera theorem, which which is saying that if f from omega to the a continuous function, such that integral over gamma f of f z t z equal to 0, where gamma is any closed curve or polygonal path in is any closed polygonal path in omega. Omega is, remember, open and connected. Okay, here we use connectedness because uh, so from one component we cannot go to the second component by using a polygonal path. So open and connected it is. So if it is the case that integral is 0, then f is holomorphic, or f has antiderivative using my internet connection is very bad. Okay, so I hope my screen is visible now. Right, then f is holomorphic, or what? How to do this? Using second fundamental theorem. If you remember, if integrals are these integrals are 0 over various or any closed polygonal path, then f has antiderivative. Okay, once it has antiderivative, so its antiderivative is holomorphic function. Its integral is, sorry, its differentiation, if you take, it will give you f. And for complex number, we have just seen that if f is once holomorphic, it is holomorphic infinitely, right? So f is holomorphic. Okay, here we are using because f prime is holomorphic. Sorry, anti antiderivative of f is holomorphic, whose derivation, if you take, is giving you f. Right. So at I think at this theorem we ended. So I have never told you higher order from higher order integral formula, higher degree integral, whatever. Uh, so other integral for cos is higher degree. People say higher degree or higher order. I'm just saying other Cauchy integral formulas. So what are these? These are nothing but uh, f nth derivative of f at given point z naught can be calculated. So n equal to 0 is the Cauchy integral formula we just saw. Uh, for other things, we just have n factorial divided by 2 pi I integral over gamma. Gamma is any curve which is homotopic to circle around z naught, and of course the circle lies inside omega, where omega is the domain of definition for f, where f is holomorphic, right? So this can be written as fz divided by z minus z naught power n plus 1 dz. uh, so n bigger than equal to 0, it works. All the formulas is here now, and so where gamma is, so we need to write gamma, where gamma is z naught plus gamma t is z naught plus r e power I t, t belonging to 0 to 2 pi, such that r is such that t z naught r, this is contained in omega, and inside omega f is holomorphic, right? So this is given. Let f omega to t be holomorphic. Then we can calculate all the derivatives at any point in terms of integral, right? So so here also again I'm saying that not only this circle, we can take any curve gamma closed curve which is surrounding z naught and is homotopic to this circle. Okay, circle of radius r, so closed curve. Okay, so now coming to our problem. I think we are recording with, so, so that those who are not here they can see that. Fine. So the first question is, let me make it bigger. So here is the first question. Omega be non-empty open connected subset of C, F, and C be holomorphic functions on omega. Assume that F is not equal to 0 function, and F is somewhere it is non-zero in this way. So which of the following statements are correct? Suppose Z naught inside omega. So first option, F of Z naught is equal to 0. So Z naught is one element which is 0 of F. Then there exists a epsilon such that f of z is non-zero inside punctured disk. So this is the theorem. If you remember, we just gone through all the details, what were things. So zeros of a holomorphic function are isolated. So this is the correct option. Once it is 0 at z naught in a neighborhood of z naught, it is not 0. Okay, so this is correct. Now what about second option? Let z set of zeros of f. There is those elements of omega where f is 0, then z does not have a limit point inside. So this is, so they do not have limit point inside omega. If they have limit point inside omega, what happens? F is completely 0. Okay, so this is the principle identity theorem. Okay, if two functions agree on a set where the set has limit point inside omega, then they are same everywhere. So this way, this is correct option. So inside omega is we require inside. Okay, the limit point can lie on boundary of the. Okay. So one example was given for B. It is necessary that they have limit points inside omega. Sorry, they do not have limit points. So there are non-trivial function or non-zero function, non-trivial function which have which which have limit point not inside omega but inside boundary of omega, which have limit point of z instead of zeros has limit point of z on the boundary of omega. So one example was given to you is kind of constructive was this that so we are taking Zn is equal to 1 minus 1 by n pi and some function f of z is equal to sine of 1 by 1 minus z. So and omega was unit is in z inside c such that mod z is less than 1. So f is holomorphic inside omega. So the problem when it is not holomorphic is exactly at point z is equal to 1. So we are taking unit is with open unit is which doesn't contain that point. So f is holomorphic there. And if you see Zn converges to 1 and 1 belongs to boundary of omega, right? But it is a non-trivial function. It is non-zero holomorphic. Okay? So this is an example which you should remember. If they have limit point inside omega, they will be zero, right? So f doesn't vanish on any subset. It has a limit point. Yeah, this is what B option is. So B and C are almost same. Now what is fourth option? Let omega be unit is, then f does not vanish on any given countably infinite subset of omega be unit is, then f does not vanish on any given countably infinite subset of omega. This is uh, it can happen, right? So this example works. Sine 1 by 1 minus z. This vanishes many times. Okay. So here n bigger than 2 you can take or whatever n bigger than equal to 1 then vanishes uh, countably many times. Okay. Vanishes uh, zn at vanishes at zn as given in the below. So this is incorrect option. Okay. Now we are going to see last part. E be a subset where F and G they're agreeing, then E has if E has limit point, then F is equal to G. This is what we discussed previously here. So if two functions agree, the set this set has limit point. So this is there are if the set where they are agreeing has limit point, then F is equal to G on omega. So this is correct. So I'm not writing the solutions for everything, but uh, what I'm discussing, you might follow, right? Most of the things were done in the class and their results proved in the class, so I'm not going to prove once more. Okay, so now coming to second question. Second question is about calculating integral, right? So how to do this type of question? So the best thing when you have 2-degree polynomial in the denominator, you can uh, factor it in one. You make it in 1 degree. So what you do? 1 upon z square plus 1. You just write this way: a divided by z minus I. So the factors of z square plus 1 are z minus I and z plus I. So what you do? A by z minus I, b by z plus I. So you calculate what is the values of a and b. So let's calculate az plus ai plus bz minus bi is equal to 1. This implies that a plus b is equal to 0 and a minus b is equal to a minus b is equal to what? ai minus bi is equal to 1. A plus b, when we are calculating coefficients of z, so a plus b, and here we have 0. So a plus b is equal to 0. ai minus bi, this is equal to 1. So this will imply a equal to minus b. We put in the second condition, then it becomes 2ai is equal to 1. So a is equal to 1 upon minus I by 2. So b is plus I by 2. Okay. So now we know. So what we get? 1 upon z square plus 1 is equal to uh, I by 2 into 1 upon z plus I minus I by 2 1 upon z minus I. Right. So now calculating integral is I. How do we do this? So what is gamma? Gamma is circle of radius 2 centered at uh, origin. So the problem is that these functions are not holomorphic at I minus I, right? So how to do this? Right. We use Cauchy integral formula. Okay. Cauchy integral formula. what we get in 1 upon 2 pi I f of z is now replaced by uh, I by 2 we can take common, no problem. 1 divided by z plus I. So okay, we separately calculate and there's no problem. 1 upon 2 pi I integral over gamma 1 upon z plus I dz. What is this? So function here fz is z plus I. So fz is 1, constant equal to 1, and we have to calculate at minus I. So what you get is this integral 1. Similarly, the integral of, right, so the other integral is same. This is equal to 1 upon 2 pi I integral over gamma. Gamma is any circle which is centered at this is gamma prime. Okay, they are not safe. Gamma prime 1 upon z minus I dz. These integrals are exactly 1. Now we just put this thing. So one thing to remember is that we are going to calculate integral in two parts, and we have to take what gamma is. So we have to draw the picture for what these curves are, gamma, gamma prime, everything. So this is, let's say, gamma 1, this is gamma 2, not, and gamma is this. This is gamma, gamma not maybe, whatever. Let's say it is gamma as given in the book. So now we draw the picture. Where are these gamma 1, gamma 2, right? So we have a big circle of radius 2, which is the gamma. So this is our I, right? So here we have gamma 2. Okay, some circle we can take of radius 1, maybe this is gamma 2, and the some circle here also is gamma 3, gamma 1. Okay, one thing that when bigger circle which is gamma can be continuously deformed to gamma 1 and gamma 2, well, while calculating the integral in parts. Okay, because for this function we only have problem at z is equal to minus I. So what happens, this kind of homotopy, so the problem is at minus I, so this homotopy does not passes through minus I, so we can deform from one surface to other. So this way, so calculating integral over gamma, so integral you have to calculate over gamma of 1 by z square plus 1 dz, right? So what you do, you replace it by corresponding, because they are homotopy, you replace here at gamma 1 I by 2 z plus I, yeah, z plus I, minus I by 2 z minus I dz. So here this integral dz, this is over gamma 1, this is over gamma 2. Okay, so fine. Now we are almost done. So these integrals are what? So put the values from here. Cos integral value you already calculated. So you take I by 2 outside into what is integral value is 1 upon 2 pi I. 2 pi I goes to the other side, so 2 pi I is here, minus again I by 2 here, as it is. The integral value is 2 pi I. 2 get cancelled, so you get minus pi plus pi. Okay, so this is 0. This is answer. Okay, so this way you why this gamma is replaced by gamma 1 and gamma 2, that's uh, the most important part. Others are not that difficult. We are just using Cauchy integral formulas to get the integrals of these parts of the function. So was that after or was fine? So this is integral is 0 and everything else is false. Now we have third question. We only have four questions, so I think we will be done in time. Today we also started half an hour late. Okay, so f is holomorphic function on a disk of radius 2 centered at 0 with let c be such that c f of 0 plus f prime at 0 be the integral of some combination of f and cos algebraic function. Which of the following statements are true? So this integral on the right side is a real integral. So how we can use complex analysis to how can we use complex analysis to get help from this? So one way we know that when we have initial, if we can take a curve, maybe unit circle that starts from 0 and ends at 2 pi, and the integral fz can be replaced by f of gamma t into gamma prime. Right? So we are going to use so let gamma t be e power I t, t running from 0 to 2 pi. So integral of fz dz over gamma, what it is? Integral of integral 0 to 2 pi f of gamma t into gamma prime t dt. This way. So this is the relation. So we have to reduce our question in this format. Then we will be, I think, will be done. Okay. Okay. So what is inside fz? So this is gamma t. So gamma t is fine. We have defined our gamma t e power I. Now we can put it here. So in e power I theta, you have to replace cos theta. So cos square theta in terms of e power I theta. How can we do this? So if you remember some formulas when cos theta was defined, cos theta is equal to e power I theta plus e power minus I theta divided by 2, right? So what we are going to do is we have to calculate cos square theta by 2. So in place of theta, we are going to put theta by 2 and we are going to take square. So cos square theta by 2 is equal to e power I theta by 2 plus e power minus I theta by 2 divided by 2 whole square. So we calculate also what is this e power I theta by 2 square will become I theta e power minus I theta plus 2 into AB, which becomes it becomes 2 only, divided by 2 square is 4. Fine. And now we have cos square theta by 2 in terms of e power I theta. So we put it here. So we have this condition. So C is such that C into f of 0 plus f prime of 0 is equal to integral over 2, sorry, 2 by pi 0 to 2 pi. So in this f of e I theta into e power I theta plus or minus I theta plus 2 by 2 theta. Okay. Now we are going to use this identity of unit circle. Then what we are going to get is this. Let's say we are writing RHS 2 by pi integral from 0 to 2 pi becomes uh, gamma. Sorry, yeah, gamma f of this e power I theta is gamma t, and what else is given here into gamma t plus 1 upon gamma t. This is so, so what are we further replace it by gamma t square. Okay, uh, this becomes 1 and plus 2 into gamma t divided by 2 2 into gamma t. Okay, now this is dt till now. So sorry, it is still we are just putting now t, so it is 0 to 2 it just becomes 3. Now if we want to use this kind of identity, so what we have to see, so some fz should be here and then gamma prime t should come. So we know that gamma t is this, so gamma prime t should be e power I t only. So gamma prime t will be I into e power I t. So where is given e power I t to be multiplied up and down by I. So this one thing is, so this 2 get cancelled with this. Okay, so this becomes 1 upon pi I. I'm going to multiply in the numerator this integrand also. Okay, 0 to 2 pi f of gamma t and into gamma t square plus 1 plus 2 gamma t divided by gamma t. Uh, Now I'm going to multiply by I e power I t means gamma t once again here. So I is already multiplied here. So this is done. Now gamma t in the denominator we have to square it. So that now this is gamma prime. Okay, so dt. Now everything is done almost. So the new function which is written here, this is what is this function? Define c of z is equal to f of z, z square So this is z plus 1 whole square, right? Z square plus 2z plus 1 divided by z square. If this is our new function, now this using this identity, you will get the actual form. Okay? What I'm telling you is this. So integral over gamma of dz, dz if you want to calculate, this will be exactly g of gamma t 0 to 2 pi gamma prime t dt, which is equal to this star. That this is star. Okay, right. So now we have a new function uh, fz into something. What we want to calculate. So if we see here in this thing, first of all, we want to calculate the value of the constant c. What is that constant? Right. So now we have this. So what we have, the RHS again. So RHS becomes 1 upon pi I integral from integral over gamma now dz, right? Dz, what is dz? Is that f of z uh, z square plus, or directly we write z plus 1 whole. If you see fz and z plus 1 whole square, both are holomorphic on omega, so their product is also holomorphic on omega, right? And what is in the denominator? Z square. So if you see, this is kind of z minus 0 whole square. Okay, integral formula says what? So this is till now everything is fine. Uh, we multiply and divide by 2. That is kind of unnecessary. But this using cos integral formula, what we get? 1 upon 2 pi I dz, or we have taken all of this. So the integral formula for f prime. Let let this be hz. Okay, hz is fz z plus 1 whole square. Then what is written inside? 1 upon pi I of hz by z square integral over gamma dz. So here I'm going to multiply by 2, divide by 2. Then this is h prime at 0. Okay. So from here, what we are able to see, h prime at 0, what it is? So this, using this, what we get here, h prime at 0. This is nothing but 1 upon pi I integral sz divided by z square dz for gamma. I think it is fine, right? Multiplying and dividing by 2, is that making any difference? Not really. So this is actually integral formula, and the function is, this is our function, 2 into sz. So the h prime at 0 into 2. This is our right. So h prime at 0 is given by, we are taking 2 this way, this side, and this is what is RHS is for our page. So from here what we get, RHS is equal to 2 into h prime at 0. Okay, what is h prime at 0? Now we calculate this coming here. So h prime at z is equal to f of z into 2z plus 1 plus z plus 1 into f prime at z. So putting that, so this will imply 2 into, if we put value z is equal to 0, so this is 2 into f of 0, sorry, f of 2 into f of 0, right? Plus when z is equal to 0, this is f prime at 0. I think there is a little mistake. So somewhere we have to check one. Let's say go through very quickly. We replace cos theta by cos e power I theta and somehow reduced our case. Uh, right, there was a little mistake. You see where here this is not 2, it is 4. It is 4, right? Cos square theta. And when we are going to get cancel this 2, this is not cancelled. This is basically, it was initially 4, but it becomes 2. So here you are getting 1 now, here you are getting 2. So in, there was some internet connection issues. Once more, let it get fixed. fine. So we were here. There were little mistakes, so we are just finding the error where there were errors. So what are we going to do for this two? Two is coming outside here, so there's no issue with that. RHS RHS becomes 2 pi I into this thing. Now we are going to use Cauchy integral formula. So Cauchy integral formula is, so let's correct it. H prime at 0 is, this is Cauchy integral formula. This bracket. Okay. So we are going to put H prime at 0. So what is H prime at 0? RHS is H prime 0 and H prime at 0 is. So now we calculate this, right? So the left hand side is actually T into f of 0 plus f prime at 0. This implies T is equal to 2. Is this correct? This is correct option, and these two are incorrect. Okay. You just see here 2 into f of 0 and plus f prime at 0. This is what we are getting. T is equal to 2. So last three options are done. How about uh, first option? Okay. So this is, let's say this is A option. So we are going to calculate first. And this is interesting part, I think. Uh, A. What is that? Integral of f e power I theta into e power I theta. You just multiply and divide by I. What happens? So the integral of 1 by 2 pi 0 to 2 pi f e power I theta into e power I theta d theta. What I am telling you is that you replace numerator and denominator and multiple of I. What happens? 0 to 2 pi f of e power I theta to I into e power I theta d theta. So this is gamma prime t and this is f of gamma t. So this can be replaced by 1 upon 2 pi I integral over gamma of gamma t into gamma prime t dt, where gamma is unit circle or e power I t. Okay, t running from 0 to pi. So what is this? F is holomorphic, right? Inside radius of, inside a disk with a disk of radius 2 at origin, and this is unit circle lying in there. So if this is, this can be replaced further with 1 upon 2 pi I integral of gamma z, sorry, fz dz, fz dz. So we have, we should write here, till now we have not replaced it. So this 0 to 2. Now integral of gamma fz dz, and because f is holomorphic, this is 0 using positive. Note that f is holomorphic on C02. This of radius 2 centered at. So part A saying this integral is 0, and that is correct. Okay. Now coming to second question. The, here in the second question, yeah, this is again Cauchy integral formula. So the part B is what they are calculating, f of 0 is equal to 1 upon 2 pi, 0 to 2 pi, f of e power I theta d theta. So what I'm going to say again, so this is the unit circle gamma, multiply and divide by I, so this becomes 1 upon 2 pi I, 0 to 2 pi, f of gamma t or gamma theta into I dt. I'm replacing theta by t, so no worries about that. What can we do to change our integral in the form of f z dz? So here somehow we have to write gamma prime t, which is I into e power I. So we're going to multiply it gamma t or e power I t with no change till now. So e power I t here, multiplying and divided by e power I t. This becomes gamma prime. So what is written here? 1 upon 2 pi I integral 0 to pi f of gamma t by gamma t I into I e power I t is gamma prime, gamma prime. So this can be replaced by 1 upon 2 pi I integral over gamma f of z divided by z. This is our function into dz. And now this is cos integral formula. This is equal to f. This is f of 0, right? Fine. So we calculated in reverse. So we just want to show what is the right hand side. We started with RHS and we are getting f of 0. This is positive. So B option is also correct. What about C option? Similar person, in the very similar person, this can be done. And here, let's say we can solve it. I think we can do this. This is for first derivative. So we start with RHS. Right. The part C, we have to show f prime at 0 is equal to 1 upon 2 pi integral uh, f of z, or sorry, is e power I t, e power minus I t dt 0 to 2 pi. So what can we do here? Nothing. You just multiply by I and divide by I. So 2 pi I is 0 to 2 pi f of e power I t divided by e power I t, yeah, into I. And we want multiply by e power I t, so that it becomes counter e power I t, and it becomes square of 2I. 2I t or square of t doesn't matter. dt. Okay. But now what it is? 1 upon 2 pi I, as it is, integral over gamma f of z divided by z square, and this is gamma prime. So this is the replacement now it is what? First derivative of f at 0. So this part is also correct. So this way we solve the third problem, and now coming to the last question. F and g be entire functions. Which of the following options are correct? If fz is non-constant, then it is found unbounded. This is correct because of Lewis. Right? If it was unbounded, then it would have been constant function because it is entire function. Now, real part of f is bounded, then f is constant. So the proof for this, real part of f is bounded. What this means? This means if you take image of f, real part of f that do not go. So what happens if you're taking, let's say, let me draw the picture here. This is first plane complex. This is our domain. Okay, and what is image? Image is bounded in real number, means the real part is bounded, means there exists some boundary of real part. So real part is not increasing. This side may be infinite, but it cannot. It is bounded by something here, right? So you can find a disk here or something where f do not have any image. So there are different ways to prove this. When how to show f is constant. If real part is bounded, then if an imaginary part is bounded, these two options are correct. Yeah. Now, so what I was going to tell you that what happens if real part is bounded or imaginary part is bounded. So the image lies in a inside a strip, or a horizontal strip or vertical strip. Strip may be infinite long, we don't care, but there exists some disk where there is no image. All the image lies outside that. So this much is required to show that f is constant. How you consider, because f do not have any image inside this disk, this is z not. So this way I'm going to tell you, but there are many other ways. So if real part, same thing will happen for of fz. This is bounded, then there exists c z not r, small r, maybe some epsilon, so that f of z, sorry, f of z do not belong to c z not r for every z inside. So fz is not going to that unit disk, means if you consider fz minus z, fz minus z naught, this function, this is holomorphic. So this is entire, this is entire, and has no zero, right? Has no zero in C. This implies 1 upon f of z naught. Why this is entire is clear, because z naught is constant and fz is already entire function. So their combination is, and when why it is not zero, because fz do not lie inside z naught. So for no value fz is equal to z, right? For no value of z, fz is equal to z. Not the case. Okay, f of z minus z naught, the modulus of this modulus is always bigger than r, because of this. Okay, so f of z minus z naught, you consider this function new function, which is cosine of the inverse of the first function. Now what is about this? This is, if you consider, this is our gz, modulus of gz, this is uh, 1 upon fz minus z naught, the modulus of this. So this is modulus of fz minus z naught, and this modulus is always less than equal to r, right? Because less than equal to 1 by r. Fine. This this implies dz is constant. Why Lewis? Okay. Yeah. Okay. Now once dz is constant, this will imply 1 upon fz minus z naught is equal to some constant c or e, whatever. It is c. So fz can be written as some constant, which depends on what p and z naught are. This is like f is fine. The real part is bounded, imaginary part. The both cases, the same proof works. Okay, for p and c. I am proving something extra. What extra? The image of holomorphic function, which is, sorry, image of entire function is dense, since it is unbounded. So what I proved is extra image of an entire function is dense in C. Okay, so real part and imaginary part both are unbounded. So if they are bounded, using label they are fine. If the real part of f is bounded, then imaginary part is also bounded, right? So if real part is bounded, then it becomes constant function, and once constant function, imaginary part is anyway the same. That is a single number, so it is bounded. Now we coming to last question. If mod f is less than mod c for every c that is c, then there exists constant p such that f is equal to same to c. This is clear, very much clear. Just how to solve mod f z is less than mod c z. This implies so modulus of is always positive. G of z modulus this is always less than 0 because this is bigger than or equal to 0 and dz is strictly bigger than f. Okay, so what happens? G of z is strictly positive, so f is entire, so fz by gz. Gz is never 0, is entire function, entire. Okay, now once this is entire function, we are going to use somehow Liouville's theorem. What to extra, so this is bounded or not. Fz divided by gz, you take modulus of this f, f by fz divided by gz. Modulus of this is less than equal to 1 using the first condition. Now what we are going to tell, uh, this is constant by Liouville's theorem. F by c fz by zz is equal to constant. This implies f is equal to c into c, and hence the proof. So it depends what c is. C is 0, non-zero, maybe some other cases, but there exists something that this is correct. Okay, so this is correct. In fact, all options are correct. Okay, so this way we have seen some of the questions. You solve more questions, and if you have any doubt, you can come to next session, and or you can email me in this email ID. Maybe when I will be free, I will do something about it. Dot at- Okay, this is my email ID. You can talk. Okay, see you next week. Bye bye.